Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 9th video lecture. And today we're going to start Chapter 6, which has to do with the Riemann-Stieltjes integral. So let me put up the title here. Riemann-Stieltjes integral. And we're going to begin by looking at some preparatory definitions to build up to the Riemann integral and then the Riemann-Stieltjes integral. So the first definition we'll talk about is we'll say let A to B be a given integral. By a partition, so that's what I'm defining, is a partition of A to B, and we're going to denote it by, so we're going to denote it by script P. We mean a finite set of points x of 0, x of 1, x of 2, all the way up to x of n, where we have that A is equal to x of 0, which is less than or equal to x of 1, which is less than or equal to x of 2, and so forth, all the way up to being less than or equal to x of n, which is equal to b. We'll do an example of this in a second. In some books, they only say less than. So here, A is equal to x of naught, x of n is equal to b, but in some books, they'll just have that x of 0 is strictly less than x of 1, which is strictly less than x of 2, and so forth. But our author is having less than or equal to requirement, which is okay. Some more notation that's involved in building up to a Riemann-Stieltjes integral is that we're going to write that delta x of I is equal to x of I minus 1. So delta x of I is the change in x's. It's the distance between two consecutive partition points. And we'll say this for I equaling 1 up to n. So as a quick example, we consider the interval minus 1 to 4. Then script P equal to the set of, let's say, minus 1, 0, 2, 3, and 4 is a partition of minus 1 to 4. This is a finite collection of numbers. The first number is x of 0, it is equal to a. The last number is x of n, in this case that's 0, 1, 2, 3, it's x of 4, and it's equal to 4, okay, which is b. This is not the only partition possible of minus 1 to 4, it's just one partition. And then also, if you wanted, you could say delta x of 1, what that would be equal to would be 0, x of 1 minus x of 1 minus 0, 1 minus 1, that's 0. And that in this case would be 0, that's x sub 1 is 0, minus x sub 0 is minus 1, so that's equal to 1. That's the distance between here. The first pair is delta x sub 2, if you like, is going to be the distance here, so I'm going to say that's 2. Delta x sub 3 is going to be this distance, which is 1, and then delta x sub 4 is going to be the distance between 3 and 4, and that's equal to 1 as well. Okay? So that's what we have. The types of functions that we're going to be talking about in terms of defining the Riemann-Stieltjes integral has to do with bounded functions. So what's a bounded function? Well, let's recall that. So a mapping, in this setting, a mapping, well, that's F. Going from A to B into R, that's the types of function. When we talk about taking the Riemann integral, the Riemann-Stieltjes integral, is bounded if there exists a positive number m such that the absolute value of f of x is going to be less than or equal to m, and that's true for all x element of A to B. We had seen examples of functions that were bounded and unbounded before, and we now want to look at another definition. This is very lengthy, but we're going to start off by letting f go from A to B into R, be a bounded function and then what we're going to say is corresponding to each partition script P of A to B, we're going to define certain symbols. And those symbols are, we put big M sub I is equal to the sup of f of x for x sub I minus 1 less than or equal to x less than or equal to x sub I. So these x sub I minus 1 and x sub i's are going to be partition points. And so we talk about that sub-interval from x sub I minus 1 to x. You look at all the x values in there, and big M sub I is the sup of the output values over that sub-interval. And we let M sub I be equal to the infimum of f of x for, again, x sub I minus 1 being less than x being less than x sub I. We know that the big M and little m sub i's will both exist because f is a bounded function. And we define the upper sum with respect to a partition P. Okay. So it's denoted by, the denotation of this is U of, it's P, script P, then F. So this upper sum depends on P and F. And it's equal to, so what it's going to be equal to, it's going to be the sum as I runs from 1 to n of, the upper sum is going to be m, big M sub I, that's that soup, times delta x sub I. That's what it's defined. And we define the lower sum and we're going to define that by L, script P of F. And what it's going to be equal to, it's going to be the sum as I runs from 1 to n of the little m sub I times delta x sub I. Okay, just as a quick example, if we let f of x be equal to x squared, and we're thinking of it being defined on, let's say, 0 to 4. And so here's what this picture looks like. So at 0, 0, 1, 2, 3, 4, at 4 we're up to 16. It looks like this. Well, I didn't draw it very well. Let's try again. Okay. Anyway, you notice the cup going up is part of it. And then let's have partition. Let's let it be pretty small. Let's have 0, 2, 3, and then 4. Okay. So when we talk about the upper sum, okay, so this is supposed to be the sum as I runs from 1 to, this would be 1, 2, 3, here 3. It's the big M sub I times the delta x sub I. And so in this case, what this is going to be equal to is you look at from 0 to 2 over here, over this sub-interval from 0 to 2. And you say, okay, out of all the output values over 0 to 2, what's the biggest one? Well, the biggest one's at f of 2, which is going to be equal to 4. And so this is equal to, the first term is 4 times delta x sub 1, delta x sub 1. I think I expand this first. So this should be m sub 1 delta x sub 1 plus m sub 2 delta x sub 2 plus m sub 3 delta x sub 3. And so as I was saying for this, it's the biggest value is 4, output value of this range, is 4 times delta x sub 1 is the distance between 0 and 2, so that's 2. And then I look between 2 and 3, that's between here. The biggest value happens, output value happens at 3, f of 3, that's 9. And so I'd have plus 9 times the delta x of 2, is just this distance, which is 1, plus, lastly, when we look at the highest value over 2 to 3 for output values, those are 16. So this will be 16, that's m sub 3, times this distance, which is 1. And so you get 8 plus 9 plus 16, it's 25, I think it's 33. Okay, the lower sum, and I'll write that here. So the lower sum is going to be equal to, okay, over 0 to 2, we take the smallest value, that's 0, times the width of this, which is 2. And then between 2 and 3, that's the next partitions, we take the lowest value, that's 4, times the width, which is 1. And then over the region from 3 to 4, the subinterval created by the consecutive partition values from 3 to 4. The smallest value here is 9, smallest output value, and that's times 1. And so that's equal to 4 plus 9 is 13. So that's an example of the upper and lower sums. Okay, progressing our way toward these intervals, we're going to find some kind of intermediate intervals, and here they are. So as a definition, we let F go from A to B into R, B, a bounded function, and 1, so this is the first definition, we define the upper Riemann interval and it's going to be denoted, we say first of all, over A to B, this closed interval, and it's denoted by so it's upper, so here's A and B, we have f of x dx. And what it's going to be equal to is the infimum of all the, over all possible partitions of A to B. Hence this infimum of, is going to be the upper sums, PF, over all partitions. And 2, we define the lowest Riemann interval as, so it's the interval from A to B. We put a little bar down here at the lower part of the interval to integrate lower of f of x dx. And what that's going to be equal to is going to be the soup over all partitions of A to B, just like what we had before now, is of the lower sums, P to F. Okay, I have a little bit more to say. Just, I'm going to write down what I said about these infimums and supremums. Where the soup over P and M over P are taken over all possible partitions of the closed interval from A to B. Now, based on those two types of Riemann intervals, the upper Riemann interval and the lower Riemann interval, we get the following definition for the Riemann interval. So here, we let F go from A to B into R, B, so every time we're talking about this, so far we're talking about a bounded function. And let the lower lower Riemann sum from A to B of f of x dx equal to the upper sum from A to B of f of x dx. Then we say f is Riemann integral integrable on the closed interval from A to B, and we designate this a certain way. So when the function is Riemann integral, and we write f is an element of Riemann integrable functions on A to B. So that's how and we could say this Riemann integral, A to B of f of x dx, is equal to, so what is this integral? That's the Riemann integral. Okay? It's equal to, well, it's either the lower Riemann integral, or you could say it's the upper Riemann integral, in this case, because they're the same. So the only time that we define the Riemann integral of f over A to B is when the lower Riemann integral is equal to the upper Riemann integral, okay, for the function. Well, there's some kind of questions here that can arise that I'd like to address. And the first thing is that we should note for each partition P of A to B, okay, and function f going from A to B into R being a bounded function. Okay. When we say that f is a bounded function, we had that earlier today, and we had it as a recall. We said that the absolute value of the output values f of x are less than or equal to some m that's positive. Well, that translates into there being two numbers, and I'm going to write down the translation. Thus, there exists maybe a little m and a big M, such that little m is less than f of x less than or equal to, which is less than or equal to big M. Okay? And that's for all x in A to B. So that's another way of saying boundedness. Okay. So we have, so this is what we've got. Well, first of all, the smallest quantity I'm going to look at is little m times b minus a. So here you're taking the smallest output value, if you will, of f of x, and you're multiplying it by the whole integral, the distance of the whole integral of a to b. So that's b minus a. Well, that's going to be less than or equal to the lower sum of p and f, which will be less than or equal to the upper sum p to f, which is going to be less than or equal to m, okay, times big M times p minus a, the biggest value we can have. And so if we look at this, and this is true for any partition P and bounded function, if we fix the function that we're talking about, we talk about the P's, the partitions changing, what we see is that the set, this, for each P, this quantity is bounded below and above that's the lower sum, and so is the upper sum, and they're numbers. So those are numbers. So what that tells us then, if you look at the set of all lower sums, partitions have overall possible partitions of the integral from a to b. If you look at that set, all those types of lower sums, and you look at the set of all the upper sums of the partition we have, over all possible partitions, that these sets are bounded. And the bounded sets of numbers. So what that says is, so the sup of L over all partitions, P of F, exists, and so does the nth of all the upper sums exist. And so what that says is, so this lower Riemann integral exists, and the upper Riemann integral exists. So we can talk about this upper Riemann integral and the lower Riemann integral. We just don't know that the function is integrable, Riemann integrable, because we don't know if these things are the same. Now, since we mentioned about these infimum and supremum, there's going to be some things I'm going to talk about to remind you about supremums and infimums in just a second. But it'd be good to do one of these Riemann integrals, and kind of one of the nicest functions to work with would be a constant function. So here's a fact. It says, if f going from a to b r, where f of x is equal to c, constant function, then the Riemann integral is going to exist. So the Riemann integral from a to b of f of x dx will be, not only will it exist, I can tell you what it is. It's the constant function times b minus a. I'm going to prove this fact. Here, we're going to let P be a partition of a to b. Okay. Then, if you look at big M sub I, for all the i's that we can have, what that's going to be equal to is going to be the sup of all the f of x's where x is sandwiched in between I minus 1 and x, not I minus 1, x of I minus 1 and x of I. Okay? That's what we have. Then, I'll say so here. Thus, big M sub I will be equal to, well, if f of x is always a constant, okay, C, then the soup over all these possible answers of output values, well, let's just C, the soup is going to be C. And similarly, little m sub I, which is equal to the infimum of the f of x over this same region, okay, it's going to be equal to C. Okay. So, if you look at the upper Riemann sum with this partition that we're looking at over out, what it's going to be equal to is going to be the sum as I runs from 1 to n by definition of m, big M sub I, times delta x sub I. Okay. Well, that's going to be equal to the sum as I runs from 1 to n of C times delta x sub I. So what is this? This is C times, let's expand this. So it's C times x sub 1 minus x sub 0, plus C times x sub 2 minus x sub 1, plus we keep going, and the last term is C times x sub n minus x sub n minus 1. Okay, so here's what I can tell you, is that the C's are in common. So I have C times each one of these. And this is x sub 1 minus, I'll write down A, plus, I pull out the C, we have x sub 2 minus x sub 1, plus, and we keep going, and the last one would be B minus x sub n minus 1. Okay, now, this x sub 1 here exists, but there's a minus x sub 1 here. And so they're going to cancel. And there's an x sub 2 here, but the next term will be x sub 3 minus x sub 2, so the x sub 2's will cancel. That continues on, so that the only things that are left are minus A and B. So this ends up being C times B minus A. So that's what the upper Riemann sum is for this particular partition, generic partition. And so, but that's what we get no matter what the partition is. So what that says is the infimum over all p's of these upper Riemann sums, well, since they're all the same as this, it's going to be equal to C times B minus A. So that says that that the upper Riemann integral of f of x, this constant dx, I'm going to write that down as constant. So a to b of c dx is really equal to c times b minus a. Well, we can go through analogous work for the lower sums. Let me write that down. I won't go through the work, I'll just write it down. Similarly, these lower sums involving partition now will be equal to C times B minus A. And that's true for any partition that we have. And so the suit of these lower sums, which equals to the lower Riemann integral from A to B of f of x dx, which is of course the lower Riemann integral of c dx. Well, that's going to be equal to, well, it's the sup of this over and over again, so that's one thing, so that's just c times b minus a. So what we see, since this lower sum of f of x dx equals to this upper sum, which equals to c times b minus a, Then, f of x equaling c is an element of the Riemann integral functions on a to b with the Riemann integral of f of x dx being equal to c times b minus a. And that's that too. Now, because we're talking about supes and infimums, I am going to review just a little bit of those items. So here's a few things. Recall, if we let E be a subset of R, B bounded above, and then suppose there exists an alpha element of R satisfying one, alpha is an upper bound for E. So what does that mean? That means for every E element of big E, E is less than or equal to alpha. And two, if you give me a gamma, if gamma is less than alpha, okay, then gamma is not an upper bound. Of E. So if those two things happen, then alpha equals to the sup of E. Similarly, we have same type of statement for infimum, so I'll write that down. So if we let E be a subset of R that is bounded below, and then suppose there exists, let's see what I have to call it, beta, there's an element of R satisfying two things. One, beta is a lower bound of E. Again, what that means is for all E element of big E, beta is less than or equal to E. And two, that if gamma, beta is less than gamma, then gamma is not a lower bound of E. Then beta equals to the infimum of E. And just one more fact. That is, if E is a subset of R and S is a subset of R, and they are both bounded sets, let's say bounded non-empty subsets of R. And for every little e into D, and for every little s in big script S, D is less than S, then turns out that the suit of E will be less than or equal to the imp of S. This fact can be useful to show be used to show eventually, okay, and we will do it in a certain setting, that that the lower Riemann interval is less than or equal to the upper Riemann interval. It's kind of funny. You know, for that to be useful, for this fact to be useful, what that means is that every lower partition is going to be smaller than every upper partition. Okay? Not when I say uppers, every lower sum is what I should say, is going to be less than or equal to every upper sum. And that's where you can interchange the partitions there. That's going to be a fact. Okay? What I want to do now is move on to some slightly more abstract definitions so that we get to something called the Riemann-Stieltjes interval. And so here's what we have. So preparatory definition, we're going to have several definitions, is we're going to start off by letting alpha be a monotonically increasing function on A to B, okay? And it follows that alpha is bounded, okay, on A to B. Okay, so alpha is going to be bounded. And then corresponding to each partition, script P of A to B, we write that delta alpha sub I is going to be equal to it's alpha of x sub I minus alpha of x sub I minus 1. And that's going to be a positive number because alpha is increasing and x sub I is bigger than x sub I minus 1. Okay? So again, that's going to be greater than or equal to 0 as alpha is increasing. That's our first definition. That's a little bit more abstract than just delta x sub I, which we had in the Riemann. Okay? The delta x sub I that we had in the Riemann intervals. Okay, so we have the delta alpha sub I. So I'm going to get 5 more definitions now. So 2, well, 2 is prefaced on this. Then for any, the rest of the definitions are prefaced on this. For any real function f that is bounded on a to b, 2, we define U, partition, F, and alpha to be equal to the sum, as I runs from 1 to n, of M sub I, so we know M sub I is defined before, delta of alpha sub I. 3, we define L, this is the lower sum of F with this partition with respect to alpha, as the sum as I runs from 1 to n of little m sub I, delta alpha sub I. 4, we have this upper Riemann-Stieltjes integral, that's what this is called, of f of x. We write down d sub alpha. Okay? And what this is equal to is infimum of the upper Riemann-Stieltjes sums here with respect to the partition D, F, and alpha. Fifthly, we have this lower Riemann-Stieltjes integral of f of x d alpha, and it's going to be equal to the sup of overall, I should have been writing partitions here, overall the lower sums, f, p, p, then f, and alpha. So here I made a slight error. Sorry. This should be the infimum over all possible partitions of A to B. So make that change. Okay, and then lastly, if this upper Riemann-Stieltjes integral with respect to alpha equals to the lower one, this should be A to B. A to B. This should be D alpha. Then we define the Riemann-Stieltjes integral of f with respect to alpha as we have the integral from A to B of f of x d alpha, which is going to be equal to, well, it's going to be this lower Riemann Riemann-Stieltjes integral, which is also equal to its upper Riemann-Stieltjes integral. Okay. And then lastly, if F is Riemann-Stieltjes integral on A to B, meaning that the upper Riemann-Stieltjes integral equals to the lower Riemann-Stieltjes integral. So, with respect to alpha, we say F is an element of Riemann-Stieltjes integral functions with respect to alpha. Ladies and gentlemen, that's enough for today. I want to thank you very much for your time and patience.